Hey there. So in our previous episode, we mentioned several sets of numbers and discussed the abstract notion of a group. And we said that some of these sets, namely the integers with respect to addition, and the rationals with respect to addition, and the rationals without zero with respect to multiplication, are groups. And we looked at it carefully and saw what the properties of being a group are and how they are satisfied by these examples. Okay? And we ended with a statement that rational numbers, the fractions, the quotients, are in fact more than just a group with respect to these two operations. They're what's called a field. So what I want to do now is first write the very, very mouthful. It's not just going to be a mouthful, it's going to be a board full of the definition of what it means to be a field. And as we write it, we're going to kind of keep the rational numbers in mind and understand that all these properties are indeed satisfied by the rational numbers. So let's get going. So here's the definition. Note that I'm reducing the font because I'm really going to fill this board. Definition. A set, So a set is now just a collection. A set F, I'm going to call it F for field, a set F with two operations, which I'm going to denote one by plus and the other by dot. I'm just too lazy to write X all the times. So these are the two operations, and you should think rationals with plus and times, with addition and multiplication. So a set with two operations is called a field. That's what I'm defining if the following hold. The following 11 axioms, 11 properties that have to be satisfied. So the first property, property number 1, for every A and B which belong to F, can you read this? For any A and B which belong to F, for any two elements, A plus B also belongs to F. So when you take the first operation, which we're going to call addition, okay, add two elements, the sum is also an element, okay? Do you agree that when you add two fractions, when you add two quotients of integers, two rational numbers, the result, I hope everybody here knows how to add fractions, okay? And you may say, ha, 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 of course we know, but just take a look and verify that you know, right? We don't just add the numerators and the denominators separately, right? We need to do a common denominator. Make sure you know how to do this. Okay, so for any two elements, the sum is also an element. What would this property be called? What is the name of this property? Right, closure. Closure. And this is closure for the plus operation. Okay, the second property still relates to the plus operation, is the associativity. For every A, B, and C which belong to F, for every three elements, A plus B plus C equals A plus B plus C. Right? So property number 2 is the associative property for addition. Okay, for the addition operation. Property number 3, note that all these properties so far are precisely the same properties for being a group. Okay? Property number 3, there exists, so property number 3 is going to be the additive identity for addition. And now we're not just going to call it E, we're just going to call it 0. Okay? There exists an element 0 in F satisfying that such that A plus 0 equals A for every A that belongs to F. Again, tell me if you can read this, if you feel comfortable with reading this. There are hardly any words in English, right? It's all math. There exists, remember this symbol? There exists a 0 element, an identity for the operation of addition. What does it mean to be an identity for the operation of addition? That when you add 0 to any element, you just retrieve that same element. It doesn't affect addition. Okay, property number 4, which is the property of having additive inverses, namely, for every, remember this symbol? For every exists. For every A in F, there exists minus A in F. That's the inverse for addition. What does it mean to be an inverse such that A plus minus A is just that identity element, is 0. Good? Everybody? Okay, so these 4 properties together read, if you think for a moment, let's look at the next board which I left from the previous clip. These 4 operations are precisely the 4 operations which say that a field is in particular an additive group. A group with respect to the operation plus. Do you agree? Does everybody see that? It's precisely these 4 properties. Good? Okay. Let's go back to this board. And I'm going to add here a 5th property of addition. Note that all these properties are still only properties of addition. And this property is saying that it's not just a group, it's a commutative group with respect to addition. Namely, for every A and B that belong to F, for any 2 elements, A plus B equals B plus A. Do you agree? Okay? So this is just one half of it. This is just the properties that say that F, a field, is just an additive commutative group. But it's more than that. And now there are going to be 5 more properties that say that these same things hold for multiplication, with the little modification that the inverses exist for any element except 0. So let's write it down. I'm going to write them a bit more quickly. So 6. For every A and B that belong to F, A times B also belongs to F. This is closure with respect to multiplication. 7. Associativity with respect to multiplication. For every A, B, and C that belong to F, A times B times C equals A times B times C. That's associativity of multiplication. 8, the existence of a multiplicative identity. There exists a 1 in F, an element which we're going to denote by 1, such that A times 1 equals A for any A in F. That's what it means to have a multiplicative identity. Property number 9. This is the property that's going to be a bit modified. So for any A not equal to 0, for any element except this 0 element from property 3, except the additive identity, there exists an element which we're going to denote by a to the power minus 1 in F, such that a times a to the minus 1 equals 1. So every element has a multiplicative inverse except 0. Except 0. Okay? So this means that a field is a group also with respect to multiplication. These are the 4 axioms of being a group, except that you need to throw out the 0 element. Okay? And then property number 10 is going to be the commutativity property of the product, of the multiplication. For every a and b in F, a times b equals b times a. So a field is also a commutative multiplicative group without the 0. Okay? And then finally, there's an 11th property, which I'm going to write down here, because it relates to both of these operations. And the 11th property we call distributivity, the distributive law. For any A, B, and C that belong to F, A times B plus C equals A times B plus A times C. This is the distributive law which binds these two operations, which otherwise would be kind of independent, right? Otherwise, you'd have a structure or a set that has two very separate structures that don't feel each other. But this says that, in fact, these structures are living together. There's a relation between the structures. Okay? Okay, so you agree that this is really a mouthful. And what you have to do now is think carefully about all of these with respect to these integers. Let's go back one board for a second. Here are the sets of numbers that we've already encountered. So Q over here was the was the rationals or the quotients. So you have to think, does Q in fact satisfy all these 11 properties? Going back here, you have to look at the properties one by one and think. Suppose we take an element. I'm looking at property number 9, for example. Suppose we take an element in Q. Let's say 4 over 5. It's not 0. Good. Does it have a multiplicative inverse? Is there an element such that 4 over 5 times that element equals 1? Right, of course. 5 over 4 is the inverse of 4 over 5, the multiplicative inverse. Okay, and you have to think about this. Otherwise, you see one big blur, right? This is really very scary, okay? But it's not. You just have to read carefully, get used to these two symbols which show up all the time, exists and for any, and this belong to sign, and decipher the abstract notion here and see that, in fact, it's really just stripping Q, stripping all these properties of addition and multiplication in Q. Okay? So let's write that. Let's write that. I think by now I can erase the definition of a group. In this course, we're going to spend a lot of time with fields. Fields are going to be the structures that we're going to consider many times. Usually they're going to be the real numbers and the complex numbers, not just rational numbers. We're not going to say too much about groups. Okay? The group was just an easier thing to pick up. It had only 4 properties rather than 11. That's why I started off with groups. Okay, so example, Q with plus and multiplication is a field. Verify. Verify that you believe all these 11 axioms. Do it. It's good practice. Okay. So the question is, are there numbers that you already know that are not rational? And right, you may have heard the word irrational, which kind of hints that there are. And what are these numbers? Give me an example of an irrational number. Right, pi is a good example. I want to discuss another one. So here's the real axis, the kind of all the numbers that you know. And suppose 0 is here. And there is a number somewhere here, which is called the square root of 2. Okay? And Pythagoras, you may have heard of Pythagoras, right? You know the Pythagorean theorem in a right triangle, right? When you take two sides, the two sides adjacent to the right angle, you take the square of one plus the square of the other, you get the square of the hypotenuse. Everybody knows that, right? So in the time of Pythagoras, this is about 2,500 years ago, in the 6th century BC, very long ago in ancient Greece, Pythagoras believed that the only numbers were rational numbers. In fact, Pythagoras and his students were actually, they made it into a religion, okay? They worshipped the numbers, the rational numbers. They thought that nature is governed by these numbers, okay? And they found very interesting relations between numbers and architecture and geometry and music and very, very interesting things. But for them, the numbers were these rational numbers, okay? What you can do with integers. And they knew the Pythagorean theorem, of course. Their leader was Pythagoras. And if you take, let's say, a right triangle with sides of length 1, that's very easy to do. Measure 1, or take a square, a 1 by 1 square, and chop it in half using the diagonal. So here's a right triangle with sides that are equal to 1. So this is 1, and this is 1. So by the theorem of Pythagoras, the length of the hypotenuse is going to be a number which squared equals 1 plus 1. So that number we're going to call root 2. So there's no doubt that this number exists. It's a real number. You can measure it on the ground or on the board or whatever. Okay? But then came along one of the students of Pythagoras. His name was Hippasus. And he said, well, this number cannot be written down as the quotient of two integers. It's not a rational number. The proof is very easy. The same proof that Hippasus gave. You can find it in Wikipedia, for example. I'm not going to do it here because it's kind of standard here in the Technion that it's done in the calculus course, so I'm going to leave it to them. But he proved it. He exhibited in a way that's really, one cannot dispute, that this number is not the quotient of two integers. You cannot find two integers whose quotient is going to square to be 2. Okay? And you know what they did? They were baffled, and then they were very disappointed. And their religion was worshipping these numbers. They took the guy and exiled him, and another theory says that they took the guy and drowned him. They just couldn't cope. But that doesn't change reality. There are numbers which are not rational, which are not in Q, and those, so all the numbers that we know form another set of numbers which we call the real numbers. Let me write that down. So this little picture proves or proves that the number root 2 is a very real number, and Hippasus proved that root 2 does not belong to the rationals. Okay? And then, therefore, there is a fourth set of number, denoted by R with a double leg, called the real numbers, or the reals. And they're called real because then there's going to be a fifth set of number, which people really couldn't believe, and they called them imaginary. Those are the complex numbers, which will follow. But the real numbers, and I'm going to cheat a bit. A formal construction of the real numbers is way beyond what we can do in this course. It's very, very delicate. I'm just going to talk to your intuition and say the real numbers are the set, remember, the set of all numbers x such that it's a point on this real line. So x is anything between infinity and minus infinity. Okay, this is really cheating, but for us it's going to suffice. Okay, so the real numbers are any real number you can think of. Okay, in particular root 2 and pi and e, if you know e from the exponent, e to the x. And all these numbers are real numbers, root 3, root 6. Some of them may be rational and others are not. A discussion of what is real and what is not. What is irrational, so not belonging to Q means it's irrational, not a ratio. The word rational comes from the word ratio. It's not a ratio. It's not a quotient of two integers. And a discussion of which numbers are and which are not is a bit more complicated, and we're not going to do it. Let's just add a few more, getting used to our symbols. So pi, the number pi, the pi from the circle, right? The way the circumference of a circle relates to its radius. So pi belongs to R. Pi is a real number, but pi does not belong to Q. So that again requires proof that pi is irrational. Pi is a real number, but not a rational number. Another way of denoting this, I'm going to introduce it, is that pi belongs to R minus Q. So this back-tilted slash here is minus of sets. So pi belongs to the reals without the rationals. So pi is irrational. Okay, is this clear? To R without the rationals. Okay, so all these are various ways of denoting. So is root 2, by the way. You can substitute root 2 here. Okay, so what one can verify, and we're going to work with it a lot. So some remarks. One, R is a field. It satisfies all the 11 axioms, and you should think about it. You should think of things that you know, but think about them in order for them to kind of to feel good with them, to feel that you understand what this statement means. So you have to go back to the definition of a field, which is whoa, and think, is it true, look at this board please, is it true that for any two numbers or any three numbers, when you add them, a plus b plus c, real numbers, root 2 plus pi plus 17, is it the same as root 2 plus pi plus 17? And you know that it is, okay? These are things that you know, but think about them. See that you actually believe them, that you actually understand these statements in concrete examples, in the context of a concrete structure, like the rationals or the reals or the complex numbers, which we're going to learn later. Okay? So R is a field. That's one statement. Another remark that I want to make is that if you look at a set which contains only one element, a set with only one element, and that element we're going to call 0. Okay? A set with only 0 in it, and you look at those 11 axioms, you're going to see that this set with one element is a field, a very boring and dull one, but it's a field. Okay? So 0 satisfies all 11 axioms, but it's so dull that usually we don't consider 0 to be a field. Okay? So usually the convention is that when we discuss a field, there have to be at least 2 elements playing the roles of 0 and 1, and they cannot be the same. But usually the convention is, usually we require, oh boy, we require that in a field 0 and 1 are not the same element. Okay, so that would force a field to have at least 2 elements, 0 and 1. And if you take the set including 0 and 1, that is a field. You can check all these 11 axioms. Okay, it is a field. So there is an entire branch of mathematics that deals with fields. Okay, but we're really just going to touch them. We're not going to go very deep into the theory of fields. It's a big theory, I just want to mention there are more fields. The first one is what we called C, the complex numbers. And these I'm leaving now as a promo for the next lectures. So we're going to discuss the complex numbers later, and in particular we're going to see that they're a field. Okay, but we first have to define them and define how we add complex numbers and how we multiply complex numbers. And then gradually we're going to see that all these 11 axioms hold for addition and multiplication of these mysterious imaginary numbers. Okay, and in fact, there are fields, there are more, but I want to mention that there are fields which we usually denote by Z sub n. Z sub n are finite fields namely fields which have only finitely many elements. So the field which has only 0 and 1 and the regular operations, but you have to be careful there. So for example, if you have only 0 and 1, what is 1 plus 1? It can't be 2 because 2 is not an element anymore. So you declare 1 plus 1 to be 0. Okay? Wow, yeah. So finite fields with the addition and the multiplication done in kind of a circular way, where you go back to where you started. It's called addition modulo n, or multiplication modulo n. This is also a topic that requires longer discussion if you want to really understand what's going on there. It's not in the scope of this course. I'm just mentioning it. Okay, so there are these finite fields. And these Zn's are only fields when n is prime. Okay, but there are fields, there are finite fields with not necessarily a prime number of elements, but that's really beyond us for now. Okay, so these are examples. So for example, Z5 is the field that contains the element 0, 1, 2, 3, and 4, where you add modulo 5. So for example, 2 plus 4 is not 6, it's 1. Because 2 plus 3 is 0, so 2 plus 4 is 1. And 2 plus 5 is 2. Okay, wow, right? Very confusing. So if you're interested in this, you can look up finite fields or ZNs in the internet and read about them. It's very cool. Very cool, and relates to many, many things you know. Okay, so for example, if you have a watch on your hand, and not a digital one, but an old-fashioned one with, a watch, a real watch, it really adds according to Z12, right? Because when you take the hour 2 and you add 11, you don't get to 13, you get to 1 again, right? So that's addition modulo 12. Okay. Anyway, that's all I want to mention about these. So the last thing I want to do is say that there are more things that are valid for fields. Many more little kind of properties that are satisfied. And the reason that we don't list them down in these 11 axioms is because we don't need to. They follow from the axioms. We can prove them knowing just the axioms. And that's what I want to do in the next clip. Kind of show you how we formally prove things in a very abstract setting. Okay? Again, it's something you have to get used to. But at first it looks, whoa, it looks like we're proving things that are, what do you need to prove here? For example, I'm going to prove that for any number, a times 0 equals 0. That's not one of the axioms. Okay, let's look at the axioms again. There's no property that says that if you take a and you multiply by the additive identity, a times 0, not a plus 0, a times 0, but a times 0 is always 0. Okay? If you think of real numbers, you know that, right? 7 times 0 is 0. 5 times 0 is 0. Pi times 0 is 0, right? But it's not an axiom here. How do you prove it? How do you show that it necessarily happens even in this abstract setting? So that's what I want to do next.